Okay, so again, in this video, I wanted to cover some problems, some questions involving vectors, and these are more related to the type of problems that you'll see in your MyOpen Math homework. Okay, so the first question says, given the vector u is equal to left bracket, right, left angle bracket, -1, comma, -6, right angle bracket. Remember, the angle brackets just represent the fact that it's a vector. So really what this is saying is that the x component of u, so like ux is -1, and then uy would be -6. Find the magnitude and angle in which the vector points. And for the angle, we want it measured counterclockwise from the positive x-axis, and we want it in radians instead of degrees in this case. All right, so how do we do a problem like this? Well, again, it always helps to draw things out, right? So if I draw out those components, I have -1 in the x and -6 in the y. So here's my Cartesian coordinate system. And I have -1 in the x and then -6 in the y. So that means the actual vector must have been like this, right? It's in the third quadrant. So it starts at the origin and goes down to that point right there. So that's my vector u. Okay, so I want to find the magnitude, the length of that vector, and I want to find this angle measured from the positive x-axis. I'll call it theta. But you shouldn't really try and find theta directly. What I would do is always find the reference angle, call it phi, find that first, and then later we can figure out the angle theta. Okay, so how do I get, let's do the magnitude of u first. How do I find that? Well, let me extract out the right triangle, right? The one that contains the reference angle. So I want this triangle right here. Where I know that this is my angle phi. This is, well, the ux was -1, but remember when we talk about triangles, they just have positive lengths of the legs, so I can just call this 1. And then the uy was -6, so this length is just 6. And I want to figure out the magnitude of u. How do I do that? Pythagorean theorem, right? So the magnitude of u is going to be the square root of 1 squared plus 6 squared. And if you work that out, you're going to get 6.08. Right, so that's the magnitude. How do I figure out the direction? Well, I can use tangent, right? In fact, you could use any of the inverse trig functions now, because you have now that you have that hypotenuse, you have all the sides. But if I just stick with the adjacent, right? Remember, the 1 is adjacent to the angle, and then the 6 is opposite. If I just stick with the original, the components, the adjacent and opposite, that's going to involve tangent, right? TOA. So I know tangent of theta, actually in this case I'm using phi, right? Tangent of phi is opposite 6 over adjacent. And then if I want phi, remember you have to do the inverse tangent of both sides. This is just 6 now, right? Inverse tan of phi is just phi. So oftentimes I don't even write all of this, right? I just write phi because I'm doing the inverse tan of tan. It's undoing the function, so I'm just getting back the argument. And then the right-hand side, you have to plug that into your calculator. But here's where you have to be careful. Because we want our answer in radians, make sure you have your calculator in radians. So I'll note that to remind you. Calculator in radians. Most of the time we use degrees, right? But occasionally a question will ask the answer in radians, so make sure your calculator is in radians. So if you work this out, you're going to get 1.41 radians. But remember, they wanted the angle measured from the positive x counterclockwise. So they want that angle theta. So to figure out theta, I need to add phi to pi, right? 180 degrees, which is the same as pi radians. So since we're in radians, to get theta, I'd have to add pi plus phi. Pi is around 3.14, or you could just use whatever your calculator gives you, plus 1.41, and that turns out to be 4.55 radians. So the magnitude is 6.08, and the direction from the positive x counterclockwise would be 4.55 radians. Okay, next question. Okay, you're told a person leaves home and walks 4 miles west, then 3 miles southwest. How far from home is she? And then in what direction must she walk to head directly home, to go back straight home? Okay, so what I would do is think of it as you're adding two vectors together, and they're like displacement vectors, right? You're undergoing a displacement. You're walking a certain distance in a certain direction. So the first one is you're walking 4 miles west. So that is in a negative x direction. And I guess I'll call this like D1 for like displacement 1. This is x, this is y. And we know that the magnitude of D1, right, the magnitude is 4 miles. Okay, so I need to find the x and y components. Well, what is the x and y components? I don't even need to use trig in this case. I can just look at it, right? Since it's pointing towards the left, it's all in the x direction, right? The entire vector is in the x direction, but it's in the negative x direction. Then I know that d1x must equal -4. And that's miles. And then what is the y component of d1? Well, none of that vector is in the y direction, so this is 0. Okay, then I do the second vector. Let's see, southwest would be like this direction, right? So I'll call this, say, D2. And I know the magnitude of D2 is 3, right? Walking 3 miles southwest. And I need to find the x and y components. So I need to find this component, which is D2x, and I need to find this component, which is D2y. Well, because I'm going exactly southwest, this angle, it must split that 90-degree angle in half, so this angle must be 45 degrees, right? So my reference angle is 45 degrees. So if I extract that triangle, the one that contains the reference angle, the hypotenuse is the magnitude, so that's 3, right? 3 miles. This is 45 degrees, and this is going to be D2x, and this will be D2y. So remember, to find the x component, as long as you use the reference angle, it's always going to involve the cosine, and the y will always involve the sine. Or you could derive that. We've done this a bunch of times. I'll assume you guys understand that part now. So D2x is going to be 3 times cosine of 45. But it's going to be negative, right? Because it's in the negative x direction. So this is going to be negative 2.12 miles. And then D2y is going to be also negative because it's going down, and it's involved the sine, right? Sine of 45. So in this case, it happens to be the same. So this is negative 2.12 miles. If I use the same notation that my open math uses, then I could say D1 is, I use angle brackets, is negative 4 comma 0, and the D2 is negative 2.12 comma negative 2.12. Okay, well, I want the net displacement, right? I want the net displacement, so I need to add those two together. I want, like, I'll call it D net. It's like my resultant, right? I usually call it resultant. I'm going to call it the net displacement in this case. So this is D1 plus D2. So in this case, right, D net is going to be negative 4 plus negative 2.12. So I'm adding these x components here, right, to get that. And then I'm going to add the y components to get that value. And if you do this, you're going to get the x component is negative 6.12, and the y component is negative 2.12. Okay, so if we draw this out, right? Remember, you should draw out the final resultant vector, in this case, your net displacement vector. We know that, first of all, we know we're going to be in the third quadrant. So it'll look something like this. So this is x, this is y, but my x component is negative and my y component is negative, a little smaller. So I'm going to end up somewhere in that third quadrant, right? So this is like my D net, the sum of my two displacements. Okay, so I want to solve for that magnitude, right? That'll tell me how far from home I am. The distance from home is the magnitude, the length of that vector. And then I also want to find this angle phi so that I can find this angle from the positive x-axis, we'll call theta, and then that will allow me to answer the second part of the question. Actually, the second part of the question is what direction would I head to go straight home again? Okay, so we'll have to think about that in a second. But let's extract our right triangle. Let me do that on another page here. So this was, let me call it phi. Okay, and again, we know that the x component of our net displacement was negative 6.12, so this length is just going to be positive 6.12. And then the y component of the net displacement was negative 2.12, so this length will just be positive 2.12. So if I want to find the magnitude of that net displacement, I'm going to use Pythagorean theorem. So this would be the square root of 6.12 squared plus 2.12. There should be a 12. Squared. And if you work that out, that's 6.48 miles. Okay, but that magnitude is the distance. So this is the distance from home, right? 6.48 miles. Now the second question was, in what direction should she head to head directly towards home again, right? What direction should she walk? What angle to head directly towards home? So we need to think about this a little bit, right? First of all, let's find the angle phi here. So I can get phi because I know the tan of phi is going to be opposite, right? So 2.12 over adjacent. So length of the opposite side divided by length of adjacent. So now, then if I want phi, I just need to do the inverse tan. Right? If I take the inverse tan to both sides, the inverse tan of the left-hand side gives me phi. The inverse tan of the right-hand side, I have to work this out in the calculator. And you should find that this is 19.1 degrees. And then really, if we wanted to find the angle that it makes with respect to the positive x-axis counterclockwise, I'm going to draw this one more time. So we found that this was 19.1 degrees. So if I want to find this angle, I would say theta. Then in this case, since I'm in the third quadrant, theta is going to be 180 plus 19.1. Right, these are degrees. So what's that? 199.1, right? 199.1 degrees. But I want to figure out, so here's my house. Think of it this way. This is like the house. And remember, I walked west for a bit, and then I walked southwest, and I ended up there. So what direction would I have to walk to go straight home? Well, I'd have to walk in this direction, right? In that direction. And if you think about it, I'll just draw it on the other side. If I subtract 180 from 199.1, that's got to give me the direction. In fact, it's just this angle, which has to also be 19.1 degrees. So the direction that she would have to walk in to get home would be 19.1 degrees. Okay, so that's that problem. And then let's do one more. Okay, so this question says, two children are throwing a ball back and forth straight across the back seat of a car. The ball is being thrown 9 miles per hour relative to the car, and the car is traveling 25 miles per hour down the road. In other words, 25 miles per hour relative to the road. If one child doesn't catch the ball and it flies out the window, in what direction does the ball fly, ignoring air resistance? And we want to give that direction in degrees measured relative to the car's forward direction. Okay, so again, we definitely have to draw a picture, right, to see what's going on here. Let's say this is the car. So I'll just draw it as like a rectangle. So here's my car. It's traveling down the road. Let's say that's the front of the car, so it's going that direction. And this velocity would be 25 miles per hour. So I'm going to say the velocity of the car relative to the ground, I'll use G for ground, is going to be, actually the magnitude of that will be 25 miles per hour, right? And this is the actual vector. So this is V of the car relative to the ground. And then the kids are in the back seat. Let's say they throw a ball. Let's say the ball is going to the right, right? And it goes out the window. So it's going in this direction. So this would be the velocity of the ball relative to the car. And that magnitude, velocity of the ball relative to the car, that's going to be 9 miles per hour. So ultimately what we want to figure out is we want to figure out the velocity of the ball relative to the ground. And it turns out to figure that out, you have to add these two velocities together, right? Because the ball already has a velocity because the car is moving at 25 miles per hour forward, and the person throws it, so it has another velocity of 9 miles per hour. So if you add those two vectors together, that'll give you the velocity of the ball relative to the ground. So it's going to be the sum of the velocity of the ball relative to the car plus the velocity of the car relative to the ground. That will give you the velocity of the ball relative to the ground. Think about, here, I'll draw a picture of how this is going to work out. This is the velocity of the ball relative to the car, right? The kids are throwing it and they throw it at 9 miles per hour. But then if I want to add that vector to the velocity of the car relative to the ground, I have to do tip to tail. So I put the tail of that vector at the tip of the velocity of the ball relative to the car. So this will be now the velocity. Let me draw that better. So this is now the velocity of the car relative to the ground. And now if I draw a vector from the tail of the first, so from the origin to the tip of the second one, that's my resultant velocity vector. But now this really is the velocity of the ball relative to the ground. And that's what I want. And ultimately, since the car is moving forward, I want the angle that it makes with the forward motion of the car. So I want this angle here. Call it theta. Okay, so how do we do this? Well, I need to find the components, right? So let's start with the component of the velocity of the ball relative to the car. So I'll draw it separately. Well, that's easy. It's just going, I'm assuming it's going to the right. So this is the velocity of the ball relative to the car. So the x component, I don't even know how to do this, maybe sub comma x. This is going to be, since all of it is moving, right, in the positive x direction, then that's just going to be 9, right? That's going to be 9 miles per hour, which you usually write as mph. And then the velocity of the ball relative to the car in the y direction, how much of that vector is in the y direction? None of it. 0. I'll just use mph here. If you want to write this in our other notation, then this is going to be angle bracket 9, 0, close angle bracket. Okay, and then the velocity of the car relative to the ground. So since it's moving forward, right, that direction, that's also pretty easy to figure out. I don't even need any trig, because I know the x direction, or the x component, how much of that vector is in the x? None of it, right? So 0. And then how much of it is in the y? All of it, and it's positive. So this would be positive 25 mph. And if I write it using the angle bracket notation, this would be the velocity of the car relative to the ground. And that's equal to 0, 25. Okay, so if I want to get the velocity of the ball relative to the ground, I just need to add these two together, right? So I add the x components together, so 9 plus 0, and then the y components, 9 plus 25, and you're going to end up with 9, 25. So that would be the components of the velocity that we want, the velocity of the ball relative to the ground. Okay, well, we already saw what that looked like, but let's finish up this problem. So we said the velocity of the ball relative to the ground is 9, 25. So if I draw this out, right, it's 9 to the right. So VB, GX is 9, really miles per hour. And then VB relative to the ground in the Y is equal to 25 mph. So the actual velocity vector is this one. Right, this is the only velocity that could have those two components, is this one right here. So that's the one we want. So this is the velocity of the ball relative to the ground. Right, after it's left the window, that would be the direction it would appear to be going. And we want this angle here, theta, because we want the angle that it makes with the progression, the forward progression of the car. So normally we find this angle, and I would again find this one, phi, because then we know we're going to use inverse tangent, right? So if I extract out my triangle involving that reference angle, the angle phi, this side is 9, this side is 25. So I know that tan of phi is 25 over 9. That means phi is going to be the inverse tan of 25 over 9. And that, if you plug that into your calculator, that's going to be 70.2 degrees. So we're saying that this angle right here is 70.2 degrees, but I really want this angle theta. So how do I find theta? Well, in this case, to get theta, I'd have to do 90, right, minus phi. So 90 minus 70.2 is going to be 19.8 degrees. And that's going to be the answer to our question, because they want to know the angle that the ball makes with respect to the forward direction of the car, and that's this angle right here. So this is going to be 19.8 degrees. So that would be the answer. All right, great. So hopefully that'll help, at least with understanding some of those questions that are in that one My Open Math section where we talk about vectors, with section 8.5. Excellent. Thanks.